and welcome to the astrO channel. Have you ever wondered what the densest object of our universe is, and how these objects can emit gravitational waves? And how did our planets evolve, and what tools can we use to analyze them? Well, in today's episode, we'll be exploring all these topics, and we'll be learning new terms such as isolated neutron stars. Now, what are isolated neutron stars, you may ask? Well, neutron stars are dense remnants of stars which come from supernovae explosions, which force protons and electrons are forced to collide into each other, forming neutrons. Thus, the name neutron stars. Now, what are isolated neutron stars? Well, isolated neutron stars, as the term suggests, is a neutron star which is lonely and doesn't interact with other objects. Now you may be asking, how do these objects produce gravitational waves? Well, that's what we'll be looking into in today's episode, and we'll be joined with a special speaker who has a project that works on the study of planets and their evolution and their interior structures. So let's get right into it. In today's episode, we are joined with theoretical astrophysicist Ankan. He is doing his postdoctoral research at the Department of Astrophysical Sciences at Princeton University. His interests include planetary evolution, gravitational waves, and neutron stars. Now, hello, Ankan, and could you please give us a brief introduction of yourself? Like, how did you end up at Princeton? What was your childhood like, and what got you into astronomy?
Hi, it's very nice meeting you, Oindrila, and thank you for the invitation. So, as a child, I was very much curious about the night sky, as everyone does, and my favorite subjects were physics and math. And I wanted to pursue both space and study physics simultaneously. And the overlap between these two gave me the joy of studying astronomy. And everything with the night sky, I was so fascinated that I decided to pursue a career in astrophysics, which is um, mostly about studying stars, galaxies, planets, everything that you see from beyond.
Okay. Well, thank you very much for that introduction, and love hearing about your interests as a child. So let's just head straight into the questions. So the first topic that we'll be addressing is neutron stars, and so how do neutron stars form, and what role do supernovae play in their creation?
Right. So the study of neutron stars was my focus during my PhD.
Okay.
Neutron stars are a very typical type of objects in space. So these are stellar remnants of massive stars. So in astronomy, we usually measure every star with respect to how much mass they have compared to the sun. So the sun has a mass which is known as one solar mass.
Okay.
Stars which are much, much bigger than our sun, which are as massive as 10 times the mass of our sun, or even 8 times the mass of our sun, when they end their lives, which means that when they run out of their nuclear fuel, which helps the sun or stars shine, there is a tug of war between the pressure and the gravity. And what happens is the gravity starts to win, and that makes the stars collapse.
Okay.
And at the end of the process, there is an outcome. So the core of these stars can live forever. So they don't die, but they are like stellar remnants.
Mhm.
They are, so as the star starts collapsing, these structures within the stars, which are atoms or even other material, get squeezed in, and they form a very compact object. And
Okay.
this compact object, which is as a first principle, um, supported by nuclear forces, a very strong nuclear force, which is how what keeps the pressure from collapsing it under the gravity produces an object which we call as neutron stars.
Okay.
And supernovae are the process by which the outer layers of the star, when it dies, it gives a huge explosion. So these are very, very energetic events in the night sky, which we observe. And as the star dies, its outer layers gets ripped off at a huge explosion, and the inner core results in a neutron star.
Wow, that was a very detailed explanation of what neutron star is. Very simple. That was really nice and interesting. And what are some physical properties of neutron stars that differentiates itself from other celestial objects?
Yeah, that's a very interesting question. And in fact, a lot of neutron star physics is hidden and it's a mysterious thing.
Yeah.
So we have studied neutron stars, and what we see is that they are the strongest magnets in our universe. What I mean by that is that they possess a very strong magnetic field that is billion times than the magnetic field that we see on Earth. And how do they get such magnetic field, how strong magnetic fields is not currently known. So it's an open question of research and people are trying to understand it. Neutron stars, the interior composition is also a mystery because there is no probe that we can have. And we have to infer from other physical effects that we observe from neutron stars and its surroundings. So what is neutron star made of? We know that it's made up of a lot of different elements, but it's also mostly neutrons, protons, and there's other different kind of species inside it. But one of the most interesting aspects of a neutron stars is that it has a very it has a structure which is composed of superconducting material, and it has superfluid material. And what are superconducting materials? Have these are objects which have temperatures which are much cooler and they have specific properties. So just to give you some brief idea of what a neutron star also looks like, neutron stars are massive. They are as massive as 1.4 times typically the mass of our sun. But they are the size, for example, a size of a city. For example, you're in Dubai, it could be the size as big as just Dubai. Can you imagine that the whole mass of the sun concentrated in that region? That
Yes.
gives rise to a very high density. So
Mm-hmm.
these objects are extremely dense and they have very fascinating physics because of this dense matter, which is from a subatomic physics point of view, and as well as very strong magnetic fields
Yeah.
which drive different processes in outside the neutron star that we
Okay.
see.
And actually, whenever I used to like watch videos on neutron stars or read about them, and they always used to say it's really, really dense. But I never knew like to scale like how dense is a neutron star really. So this really put it up to scale. And actually, my next question is kind of theoretical. It's not really anything we researched about, but it's like I've stumbled upon it where we know like this is kind of based on Einstein's general theory of relativity, where he says that we have a space-time fabric and that all objects, like all astronomical objects, like warp that space-time fabric. And whenever I see a neutron stars, warping it goes all the way down. I'll also be showing a picture of that. But so my question is, I've seen that some people have said that what happens if that neutron star tears the fabric of space-time? Will it create a wormhole, or will well, that's what would happen?
Right. So So as you pointed out, Einstein's general theory of relativity is a theory which gives how matter curves the space
Yeah.
time around it. And the phenomena that you are referring to is caused mostly by an object which are known as black holes.
Yes.
So black holes are also another outcome of the death of massive stars. These have to be a little bit more mass. For example, I told neutron stars are formed from stars which are 10 times the mass of our sun. If the star is much larger than that, if the star is 20 times the mass of our sun, that star ends its life by forming a black hole.
Yeah.
And that black hole is a region in space-time where there is a singularity and the fabric of space-time gets infinitely curved at that region. Unfortunately, neutron stars are not strong enough to tear the fabric of
Okay.
space-time. But it's an interesting question, and a lot of physics breaks down at that
Mhm.
point.
Yes, like even when they say like when the black hole singularity, when you go down there, like gravity becomes infinite, the physics, mathematical equations all break down. So
That's
it's
right.
something really interesting to think about. So I just wanted to see your view on it.
Yeah.
So our next topic that we'll be shifting to is gravitational waves. But actually, what I really wanted to know was how can, I mean, I think you introduced a term called that I saw was isolated neutron stars, which, first of all, could you maybe explain what it is? And also, how could isolated neutron stars emit gravitational waves?
Yeah, that's a very good question. And as you have pointed out, Einstein's theory of relativity, and that has to do like if matter curves the space-time around it, and they
Mm-hmm.
can also send ripples in this fabric, right? So I studied isolated neutron stars. So these, when I talk about isolated neutron stars in the context of gravitational waves, which are ripples in the fabric of space-time, so there are two kinds of gravitational waves, or two sources.
Okay.
The one type that we have detected are sources from compact binary coalescences. So
Mm-hmm.
these are two compact objects. You need to have two compact objects like two neutron stars or two black holes which orbit around each other.
Mm-hmm.
They lose energy and they collide. And
Okay.
that when they collide, they emit
Okay.
gravitational waves. This is the one type of source that we as humans have been able to detect through a
Mhm.
detector known as LIGO.
Yes.
Now there are other type of sources because any source can curve the fabric of space-time,
Mm-hmm.
but the strength of gravitational waves might not be strong enough. So one other possibility is that neutron stars, which are isolated, which means that if you have just one neutron star, maybe in an X-ray binary, an X-ray binary is a system where you have a one compact object, and a star which is orbiting this compact object. So
Okay.
it's the other object may not be a
Mm-hmm.
right. So in these kind of systems, so the isolated means that you have one neutron star involved, and when there is a single neutron star, there can be processes on the surface of the neutron star or within the outer crust of the neutron star to possess deformity. So what I
Okay.
mean by so neutron star material is also deformable, and that can happen when there is some asymmetry in the mass distribution through magnetic fields or through accretion. Accretion means that these objects have some material inflow from their surroundings on their
Mm-hmm.
surface. And when that happens, this material gets pushed inside, but due to heating effect, there
Okay.
is deformed layers of matter,
Mm-hmm.
and these neutron stars are also spinning. So if these
Okay. Yeah.
objects spin very fast and you form what we know as a mountain, just like the mountains that you see on Earth, in that case, a neutron star has a property which we call as a quadrupole moment, which means that there is some asymmetric distribution of matter on their surface, and they are spinning very rapidly. And that's how, if you have an quadrupole moment, that gives rise to emission of gravitational waves.
Okay. So wow, so there are a lot of different sources. I knew about the binary pairs, but I didn't know about this quadruple or like quadruple, I think. And,
Moment, yes.
yes, and I was actually thinking a little bit about pulsars, but I don't think pulsars are, or are
Right,
they connected?
right. So pulsars are a class of neutron stars
Hmm.
which emit pulsating radio waves.
Okay,
So what
yes.
I mean by pulsating radio waves is that they form jets from
Mhm.
the magnetic poles. So
Yeah.
these are radio waves, which
Hmm.
and as it's spinning, the effect is that of a lighthouse. We call this as a lighthouse effect. So if you have
Okay.
seen a lighthouse where
Hmm.
there's two beams which rotate,
Hmm.
and as it crosses Earth, we will see a flash of light.
Okay.
And this is very periodic because these flashes of light come after a regular interval of time. So there is a
Oh,
periodicity associated with the
okay.
neutron star and the pulsar that we call. So
Okay.
pulsars are pulsating neutron stars.
Yes. Well, okay, that was a really, really nice example, and actually, I learned a lot from that because it was very simplified, so I also understood much of that. So I think you already answered this question, but it's actually related to like what type of technological tools can we use to detect these gravitational waves from neutron stars? So like we already had do for the other gravitational wave that we detected from different sources, but this is an isolated neutron star. So
Yeah,
how might we detect this one?
yeah, absolutely. So LIGO
Mm-hmm.
operates at a particular bandwidth. So the
Okay.
bandwidth that it operates is that it is sensitive to a particular frequency. Whereas the isolated neutron stars emit at a different frequency
Okay.
than the LIGO band,
Mm-hmm.
current at the current sensitivity. So one needs an advanced detector, or one needs to have an improvement to the current technology
Mm-hmm.
which people are working on. And there is a mission which is in the future, which is called the Einstein telescope.
Yeah.
This is a telescope, or it's a gravitational wave observatory in Europe, and there's one in the US which is also under
Mm-hmm.
commission, that is called the Cosmic Explorer. So these two detectors in the future, which will be able to detect low frequency gravitational waves, they will be able to detect a large amount of a lot of other sources as well. So one of the possible sources would be these isolated neutron stars.
Wow, well, I'm really looking forward to these new projects that might be happening in the future, and hopefully, I'll get to maybe work in some of them.
Yeah.
But now I'd like to get into planetary evolution. So, as you may know, that Ankan has a project which works called Apple, which works on the interior structures and evolution of planetary. So maybe could you give us a brief, just not too technical, like what Apple is and how it helps in looking at or analyzing planets and their evolution?
Yes. So Apple is an acronym.
Okay.
It stands for a Python code for planetary evolution.
Hmm.
So it's a code which solves the interior structures of planets
Mhm.
based on the theory of stellar evolution or planetary evolution. What I mean by that is that it gives you the history of how planets have evolved. What I mean by that is it gives you the cooling history. So planets, when they form, they are very hot and they cool down as
Mhm.
as they age. As it cools down, its temperature decreases, and we measure them currently. If we detect a planet, we we measure its temperature. These are the temperatures at the surface. We can also measure temperatures of planets in our solar system. For example, we can measure the temperature of Jupiter, we can measure the temperature of Saturn. We can also measure their atmospheric composition. So, for example, Earth has an atmosphere of nitrogen, oxygen, and carbon dioxide. These planets also have an atmosphere, which are made up of different elements, different molecules. So, what is the composition? How do you know that this is the type of composition that planet will have, and that what temperature it will have? How big is the planet? How massive is the planet? So these are the type of questions that one can answer with
Mhm.
with this type of the code that we have developed here.
Well, also, could this code maybe help analyze or detect exoplanets, maybe in our galaxy or maybe around us?
Yes. So in terms of detection, well, let's put it this way. We can predict certain compositional structures or atmospheres present in these type of planets from our theoretical models. If we know that if we see some features like molecules in the atmosphere, there's a very distinct signature in its spectra. So a spectra is the flux that we receive from these planets.
Mhm.
Flux means the light that comes out as reflected from that planet and that we observe. And they have very distinct signatures. And if our theoretical models based on a particular structure predicts that there could be ammonia present in this type of atmosphere, we
Mhm.
can go and search these kind of planets and see whether they actually exist or not. So maybe
Yeah.
that's one of the ways one can probably
That
use this technology.
yes, and it's pretty clear that these computer simulations and mathematical models really help in looking into and understanding planetary evolution. And also, this could help us kind of look into if Mars is inhabitable or not as well, if that could, or no,
Uh,
because
uh, that that question is extremely difficult because
yeah,
we are not yet there,
I know.
and our current understanding or the kind of physics that we study from these basics, very simple models,
Hmm.
at least for scientists like us, is extremely challenging. There are, however, engineers in NASA who are at a better understanding of what is required because a lot has to do with geology, what has to do with atmospheres in these planets, and whether they are habitable or not, because it depends on the temperature and it also depends on the amount of oxygen present and then
Yeah.
the other effects such as heat and whatnot.
Yes. And actually, since we've talked a lot about planets, magnetic fields, and gravitational waves, I also wanted to date back to a incident that happened a few months ago, which was about northern lights, which are basically solar flares that are emitted from the sun's corona. And the only reason we aren't affected by completely is because of our Earth's magnetic field. So when the solar flare tries to come in, it just gets deflected from its path. But the only 2 points that it can enter is the North and South Pole. So, actually, a few months ago, it was said that we were able to see northern lights from places that weren't even, where that are really rare to see northern lights. So maybe how could my question is why could this be? What is it because maybe our Earth's magnetic field is weakening, or I just wanted to know your view as like a person working on astrophysics.
Yeah, that's a very interesting point, and it's kind of also fascinating. So what happens in the sun is that sun has a lot of magnetic activity
Mhm.
going on in its interior and it's on its surface. So the sun also has a magnetic field, as our Earth also does.
Mhm.
And as you mentioned about coronal mass ejections, which is a process by which the magnetic fields on the surface of the sun is tangled, and they don't like to be tangled all the time, and they break apart. And as
Mhm.
these two loops or knots they break, they release a lot of plasma
Mhm.
and a lot of mass.
Yeah.
And these charged particles travel at extremely high speeds,
Mhm.
which are emitted from the surface of the star or the sun, and they travel in the solar system. And they go, and it's kind of a storm that happens. There's a storm that comes, and these charged particles travel at an extremely high speed. Usually, the Earth's magnetic field is strong enough at the other places,
Yes.
depending on its structure, and these charged particles follow the magnetic field lines, and as the magnetic field lines close at the poles, they
Mhm.
enter through the poles, and that's how we see the different
Northern light.
northern lights at the different poles. However, it depends on the energy of these charged particles, and if they are very, very energetic, they can actually penetrate even from other places.
Okay.
And that depends on what is the activity that goes on in the sun. And
Mhm.
there could be processes in which it is extremely energetic. That can cause a very large storm to come, and that will
Mhm.
create the uh, the, the penetration of these charged particles from not only from the poles but also from other places. It depends on what angle it's coming at.
Okay, well, that's a really interesting point of view on this, and hopefully, because these can also be very dangerous to our atmosphere as well. So hopefully, this maybe doesn't, maybe actually is very unpredictable, I think. Because is there any um people who are like looking into maybe the behavior of these solar flares, or is it just completely unpredictable for us to know when we're gonna get a really big solar storm?
Right. So people who study this can actually study the movement of
Mhm.
sunspots, which are regions where
Yeah.
this kind of things can happen. But there is a regular cycle in the sun from which is also very predictable. So there's a cycle of magnetic, which is known as the solar magnetic cycle, which happens every 11 years.
Hmm.
But this there could be other activities emerging randomly, but that already shows up maybe few months between or even a year time scale, and people study that and they can predict this can happen very soon. And it's very unfortunate because we don't have the technology
Yeah.
to prevent ourselves. And if a storm someday comes and hits us, it can knock off all the electronic systems on our planet, and it's very dangerous.
Yes. Well, thank you for saying your point of view on this topic. So, as we reach the end, I actually wanted to ask what may be your like advice or maybe notes on people who actually want to get on this astrophysics journey and what might they want to achieve before and what might like help them get on this journey of astrophysics.
Yes, so I think the first is a curiosity. You should be curious about what's happening around you, what's happening beyond our Earth. That's the first thing. I think we as humans should always be very curious and raise questions about how are we here? What are we made of? What is the meaning of our existence? Are we alone? Are we the only living beings? So these type of questions will get you started or get you feel interested about the subject. And then on a realistic point of view, for high school students, one should focus on physics because that's a very important topic which will help you do research in the long run.
Mm-hmm.
It's also important to know mathematics. That's
Yeah.
another aspect because it's a tool that helps us solve equations.
Yes.
And nowadays, a lot of astrophysics is heavy computation dependent. Whether
Yeah.
you're doing observations or you're doing theory, the era of pen and paper work
Mm-hmm.
is almost over, and
Okay.
we are moving to an era where we are heavily dependent on technology. And to know a little bit about computer science, about programming,
Yes.
will extremely help you in doing research in astrophysics.
Yes. Yes.
And yes, I think if one gets started with these, I used to read a lot of popular science books. For example, books by Stephen Hawking, there's books by Michio Kaku, there's books by Brian Greene. These were the books
Yes.
when
Yes.
I read when I was in high school,
Mm-hmm.
and that helped me get an interest in the subject. And then I focused on physics, I focused on computer science in my professional or in
Mm-hmm.
my career journey, and I did a lot of internships
Yeah.
locally with professors. And if you get an experience of what goes on as a hands-on experience on how to do
Yeah.
research,
Yeah.
that is the way you will, in the end, be extremely beneficial and helpful to have a career in astrophysics.
Yes, actually, before, like, I had an interest in astrophysics, but I wasn't really interested in like coding and computer. And then when I realized that astrophysics really relied on this, then I started doing courses. And I think it's really gonna help because I understood the role. Plus, I can see how impactful your project Apple is as well in predicting these things in astronomy. So I think these points are really helpful. And also the books, there's a lot of books that I think encourage astronomy and just talk in simple terms, like for instance a sci-fi like Isaac Asimov. I think
Oh, yes.
he's really influential, which I've also been reading a lot. So I think these points I will keep in mind because this has been a huge learning for me, and I'm also really interested in neutron stars and your work as well. And I have I'm honored that you joined us today on the Astro podcast. So thank you very much, and hopefully we have the pleasure of being joined with you again on our show. On our-
Thank you very much, Oindrila, for inviting me again. I had a lovely time and I wish you all the best. And
Thank
probably we might end up seeing each other and work together in the future.
Yes. Well, thank you very much. Have a nice day.
Thank you.